Chemists are frequently involved in either producing completely new compounds or developing alternative methods of producing well-established compounds. In either case, it's obviously essential that we're able to identify accurately any compound we produce in the laboratory. Chemical tests are usually destructive and could easily use up several weeks' worth of new material in one go. As well as being destructive, these tests can only give us a guide to the functional groups present in any compound. But modern science now demands much more detailed information about chemical structures. Nuclear magnetic resonance spectroscopy, or NMR, offers us a valuable means of obtaining the detailed information that's now required of us. We usually run an NMR spectrum to determine the structure of a molecule whose empirical formula we already know, normally obtained by also having a mass spectrum run on the compound. It's a non-destructive technique used extensively in chemistry to determine the detailed structure of unknown compounds. So, what exactly is nuclear magnetic resonance, and how does it identify molecular structures with such certainty? Just what can we learn from a spectrum like this? NMR spectroscopy depends on a few simple physical properties. Nuclei are made up of particles that have a property called spin, and these are only able to spin in one of two ways. You may hear this called alpha and beta, clockwise and anti-clockwise, or positive and negative. But in this video we'll use the terms spin up and spin down. The important thing is that they are exact opposites of each other. Particles of opposite spin can pair up in the nucleus. However, when there's an odd number of particles present, the nucleus is bound to be left with a residual spin. Spinning nuclear particles also have associated magnetic properties. Of course, their spin state could be either spin up or spin down. Nuclei which display NMR activity do so because of this residual spin, or rather its associated magnetic properties which the spectrometer can detect. Which is why we refer to nuclear magnetic resonance. So, in general, it's nuclei with odd mass numbers that have suitable magnetic properties, and the most commonly used nuclei in NMR spectroscopy are carbon-13, nitrogen-15, fluorine-19, phosphorus-31, and the proton. In this video, we're only going to deal with the detection of the last one of these nuclei, the proton, but the same basic principles obviously apply when NMR is used for detecting any other nucleus. Although in NMR we refer to protons for convenience, organic molecules actually contain covalently bonded hydrogen atoms, not free protons. So, how does NMR detect the nuclear magnetic properties, and how can we work out the structure of a compound from the information we receive from a spectrum? The sample we put in the NMR machine is usually in solution, but it's best if the solvent used doesn't give any signals of its own on the spectrum. So, for proton NMR, we need a solvent without any hydrogens in it. Deuterated solvents such as CdCl3 are commonly used. In a sample, proton spins would normally be a random collection of both spin-up and spin-down states. If we put our sample into a powerful magnetic field, protons in the spin-up state align with the field, whereas protons in the spin-down state oppose it. The applied intense magnetic field used in NMR spectroscopy is created by a superconducting magnet, cooled to around 4 Kelvin using liquid helium. Protons aligned with the field, spin up, have a slightly lower energy than protons opposed to it, spin down. So the spin-up protons go into a lower energy level, and the spin-down protons go into a higher energy level. The difference in energies is referred to as the energy gap. Such energy gaps correspond to energies found in the radio frequency band of the electromagnetic spectrum. When the spectrometer generates exactly the right frequency, and this hits a particular proton, it absorbs some of the energy, causing it to flip from one level to the other. This condition is known as resonance, and it is this that the NMR spectrometer detects. The bigger the energy gap, the higher the frequency needed for resonance. The magnetic field which causes resonance isn't simply the field applied by the electromagnet, it's actually the local field sensed by the nucleus, which is often a little different. This is because the electron clouds near the nucleus modify the applied field, so that hydrogens in different chemical groups come to resonance at slightly different frequencies. For instance, this hydrogen on a methyl group resonates at a different frequency from this hydrogen on a hydroxyl group, because their chemical environments are different. Because the various protons in a molecule require different energies to resonate, the spectrometer sweeps across a whole range of frequencies, recording the absorption at each frequency, and displaying this as a series of peaks on a spectrum. So, in other words, a record of the different frequencies at which protons resonate in a given sample will give a clue to the various chemical environments of hydrogen atoms in the molecule, and so help us to determine its detailed chemical structure. Having outlined the basic principles involved, let's look now at how we interpret an NMR spectrum. Along the bottom of the spectrum is a scale, increasing from right to left, with 0 at the far right. It is along this axis that the peaks, representing different resonance frequencies, appear. The axis, however, is not scaled in frequency units, because the actual frequencies where resonance occurs depend on the strength of the applied magnetic field, and so will vary from instrument to instrument. To allow for instrument variation, the axis is scaled as a dimensionless quantity, simply the difference between the observed resonance frequency, nu, and a reference frequency, nu ref, rendered dimensionless by dividing by nu ref. This removes field dependency. Multiplying by 10 to the 6 brings most protons onto a scale of roughly 0 to 12. This scale is known as the delta scale. The position of a peak along this axis is referred to as chemical shift and is measured in parts per million or ppm. The common standard chosen for the reference frequency in proton NMR is tetramethylsilane or TMS. TMS is chosen because it has 12 protons, all of which are chemically equivalent and all resonate at the same frequency. It is also chemically inert, volatile, therefore easily removed, and has its own single intense resonance in a region well away from most protons in organic molecules. 0 on the delta scale falls at this reference peak. So, let's see what we can learn from a basic spectrum looked at in low resolution. If we look at ethanol, with the empirical formula C2H6O, a basic spectrum would look something like this. We know from the empirical formula that there are at least 6 protons, yet the spectrum gives only 3 peaks. Why? Remember, all protons in the same chemical environment will resonate at the same frequency, giving only 1 peak. So the number of peaks shows how many kinds of non-equivalent protons are present, not how many protons. 3 peaks indicate that there are protons in 3 different chemical environments. But how many are in each? The peaks have different heights or different intensities, and by calculating the areas under each peak, known as integration, we can determine the relative number of protons each peak represents. The spectrometer performs the necessary calculations and presents the results as integration traces on the spectrum. These are shown as a series of steps, with the height of each step being proportional to the number of hydrogen atoms associated with each resonance. In fact, in our sample, we find a ratio of 1 to 2 to 3. You must remember, however, integration indicates the ratio of protons represented by each peak, not the actual number of protons. Since the ethanol molecule contains only 6 protons, we can assign the peaks to 1 proton, 2 protons, and 3 protons. The position of each peak on the delta scale, its chemical shift, gives us an indication of the chemical environment of the protons involved. In general, the closer a proton is to an electronegative element, such as oxygen, the greater the chemical shift that proton will experience. As you'd expect, there are tables available that indicate the range of shifts of typical protons in different chemical groups. So, in ethanol, the proton that is shifted most is the hydroxyl proton, due to the closeness of the electronegative oxygen atom. Referring to the table of chemical shifts, we see that the 2 hydrogens are part of a methylene group joined to an oxygen, and the 3 hydrogens are on a methyl group. So, we've learned that the total number of peaks, or absorptions, indicates how many kinds of non-equivalent protons are present. The area under each peak, integration, reveals the proportions of protons that are associated with each peak. And the chemical shift, the position of each peak on the delta scale, gives clues about the environment of each kind of proton. What we've considered so far has been a simplified picture. In reality, all NMR spectrometers produce high-resolution spectra. These give us even more detailed information about the structure of a molecule. If we now look at a high-resolution spectrum for ethanol, we see that 2 of the absorptions are in fact multiple peaks, although the overall integration traces are the same as before. The CH3 signal is split into 3 peaks, known as a triplet, and the CH2 signal appears as 4 peaks, a quartet. This splitting of the signals results from interactions involving the spins of neighboring protons. The spin of a proton under observation can couple with the spins of adjacent non-equivalent protons. This is known as spin-spin coupling, and its effects help us to determine the relationship of groups within a molecule. Spin-spin coupling affects the magnetic field at a nucleus, giving rise to several possibilities. We know that the spin of a proton will be aligned either against the applied magnetic field or with it. If this proton is affected by spin-spin coupling with a single adjacent proton, the spin of the adjacent proton could also either be aligned with our first proton or opposed to it. The effect of this spin-spin coupling is either a very slight increase or a very slight decrease in the resonance frequency of our observed proton. So from one adjacent proton, we have 2 possible effects. Because of the vast numbers of molecules, and therefore protons, in an actual sample used in a spectrometer, both possibilities are bound to be present. So the resonance shows as two peaks, a doublet, on the spectrum, and the center line between these two peaks is the position of the chemical shift. If we have spin-spin coupling with two adjacent protons, we have more possibilities. The adjacent protons could both be aligned with our first proton, or they could both be opposed, or one could be aligned with and the other opposed. There are two ways of this happening, but both will create the same effect. So from two adjacent protons, we have three possible effects, and this will show as a 1-2-1 triplet on the spectrum, the center peak having double intensity, representing the two equivalent options. With three adjacent protons, we have even more options. This results in a 1-3-3-1 quartet on the spectrum. We can see a definite pattern here. As a general rule of thumb, when a signal is split into multiple peaks, the number of peaks equals the number of adjacent non-equivalent protons n plus 1. So, if we go back to our high-resolution spectrum of ethanol, we can now understand why we have multiple signals. The CH3 group is registering as a triplet in the ratio of 1-2-1 because it's being influenced by spin-spin coupling from the two protons in the CH2 group. Remember the n plus 1 rule. Whilst the CH2 group shows as a 1-3-3-1 quartet, being adjacent to the three protons in the CH3 group. The hydroxyl proton is a special case and doesn't undergo spin-spin coupling, so remains as a single peak. So finally, let's recap on the basic techniques we've now learned. Firstly, NMR spectroscopy is used for compounds whose empirical formula is already known. For proton NMR, our sample needs to be in a proton-free solvent. Usually, a deuterated solvent is used. The NMR spectrum shows a scale increasing from right to left. This is known as the delta scale, with 0 set to a reference standard, and in proton NMR the standard used is tetramethylsilane, TMS. There are four important aspects of NMR spectra which provide valuable information about chemical structure. The number of peaks, or absorptions, indicates how many different kinds of chemical environments are present. That is, how many different kinds of non-equivalent protons there are. By integration of the areas under these peaks, we can allocate the proportion of protons that are associated with each peak. The chemical shift, the position of each peak on the delta scale, gives clues about the environment of each kind of proton. Finally, the splitting of an absorption into several peaks, due to spin-spin coupling, provides information about neighboring groups. Remember the n plus 1 rule. From all this information, the detailed structure of a molecule can be determined. In this program, we have dealt solely with proton NMR, but the basic principles described are commonly applied to detect other nuclei such as carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. The detailed information provided by NMR spectroscopy has become an essential tool in the chemistry lab, enabling chemists to confirm that the molecule produced is exactly what is required. But NMR also has important applications beyond the laboratory. One of the most effective applications is in the area of medicine, where magnetic resonance imaging uses the same principle for detecting different nuclei in the body. However, Rather than produce a spectrum, the resonances are converted into visual images that represent sections through the body. Different soft tissue types can then be identified and abnormalities detected.